Okay. Hi. Today I am going to try to explain a method that I use to balance rotors or moving, rotating parts, such as this one, which is a whirligig that I am building. And you can notice that the rotor is made out of wood and it rotates. And the idea is that if it's balanced, it won't oscillate when it stops. So what I've done here is I use small weights such as these coins and washers, different size washers, another coin here and another washer, and I weigh them in this scale. If I don't know, I use a scale like this one. So I just weigh them, and hopefully this scale would have a 0.1 gram precision. And so I use them, and then with this method I can determine how much weight do I have to put in one place or in two places so that the rotor is balanced. Okay, so in this case, for this rotor, which has 4 blades and it's made out of wood, 45-degree the wind is not very powerful in this area, so if it's going to work, it must be balanced, because otherwise it would require too much wind for it to start running. Okay, so here I have another example, which is wood gear, and you can tell here I'm going to make it rotate, and it's as I am showing, it's unbalanced. And you can tell because it starts oscillating. You see? Now, if I repeat this over and over, I can find the line, the equilibrium line, which it will stop every time, which is this thick line that I have drawn here. Okay? So what I have done, or what you need to do in this method, is to get a testing weight, and I'll put it in this, for this matter I'll put it here. Okay, and you will see that the equilibrium line changes. So I'll have this rotate. Okay, so now you can see that the equilibrium vertical line is this one now, instead of that one, which was the one I showed previously. It's this one. Okay, and I also know how much weight I put here, and also the angle relative to the first and second lines. So with these, I measure these with a protractor. I can measure these some way, have these angles measured, and with these angles I can figure out how much weight to put anywhere in the rotor so I can balance this. For example, in this case, I would probably could solve the problem putting a weight here, but probably the weight that it'll request me, the method, is probably will not be available. So I prefer to set points, this point and this point, to this point and this point put the balancing weights so that I can use I can split the weights and use a standard or use the balancing weights that I have at hand. Okay. So remember, when it's unbalanced, the first line, vertical line, I will have to figure it out and identify it, and then with the reference weight, I'll have a second line. And the angle between both of them is very important because it'll allow me to calculate what the balancing weights are in this wheel, as you will see in the next images. Okay, so this is a wood gear that I cut in the scroll saw, and I want it to be balanced also because it's for a wooden clock, and the wooden clock, you need to have the wheels relatively well balanced so that the energy consumption doesn't need too much torque to start, because the problem with unbalanced rotor is that you need to, when you start at slow speeds, you need to overcome the unbalanced torque, which may be too high for the driving mechanisms, or for the motor, or for the weight that you're using to move the wooden clock, for example. Okay. Now I show you the results of the balancing method. You can see here in the images that the gear is rotating, and it stops randomly without repeating the position, which means that it's balanced statically. So it'll stop at any given position without oscillating back to a fixed equilibrium position. Now I will discuss the mathematics of this method for balancing a rotor. The dashed line it represents the boundary of the unbalanced body, and mx represents the unbalanced mass, or the eccentric mass, and Lx represents its position relative to the axis of rotation. So if I rotate the body and let it stop freely, it will repeatedly end up stopping at this line of equilibrium, which we will call L1. Okay, so how can I compute, how can I measure the amount of eccentric mass mx and its distance relative to the axis of rotation? Okay, so what we do is that we mount a reference mass at an angle theta r relative to equilibrium line L1, and at a radial distance LR. Okay, and once I do that, I will let the body rotate and stop freely, and it'll stop after trying out many times. It'll stop always at the same position, a new position, which I call L2. So I will mark then L2 in the rotor
as well as already marked line L1. And line L1 and L2, there is an angle theta x relative to each other, and the angle theta r is the angle in which I mount the reference mass relative to line L1. So the equilibrium equation, the torque equilibrium equation, respect to the axis of rotation would be given by this expression. And so, since in these expressions I know how much the reference mass I used and the position, the angular, and the radial distance, I can isolate the value of mx Lx as shown in this expression. So this expression now allows me to know the value, the magnitude of the end balance of this rotor, which is mx Lx, and it's all given in terms of things that I know previously or I can measure, such as the angle theta x. Okay, once I know that, I can put a new balancing mass along line 1, so that mx Lx will be equal to m1 L1. But so that would balance the rotor. But oftentimes it is not possible to put the balancing line in the same line L1 because there's no space, or there's a collision with another object, and so on. So usually you have to use two balancing masses. In this case, I show M1 and M2, each one at a radial distance and at an angle relative to the reference line L1, or the horizontal line which is perpendicular to L1. Okay, so now with these three masses, their center of gravity of these three masses has to be at the axis of rotation if it is going to be balanced. So the equations for the center of gravity are, this is for the x axis and this is for the y axis. So if I select values of L1 and theta 1 and L2 and theta 2, then this is a system of equations with two unknowns, M1 and M2. So I can isolate their values using these and I obtained the formulas to compute them. This one for M1 and this one for M2. Okay, so once I compute M1 and M2, I can place these masses into the positions I have used for the computation, L1 theta 1, L2 theta 2. Okay, let's do an example. For example, I have a mass rotor with an unbalanced mass, and I let it rotate and stop freely, and then when it stops, I will mark line L1, which is the vertical equilibrium line. I know that the eccentric mass or the unbalanced mass lies along this line. The second step is to select a reference mass and install it mounted into the rotor at an arbitrary position. For example, in this case, I have used 10 grams as a reference mass, and I have put it at a radial distance of 12 centimeters and at an angle of 100 degrees relative to line L1. Once I do that, I make the rotor rotate and stop freely. When it stops freely, I will have a vertical equilibrium line, which I will mark in the rotor, and I will measure the line between L1 and L2, and let's say, for example, it were 30 degrees. Okay. With this value, I can compute the unbalance, the values of mx Lx, using the formula, the expression given in the previous slide. So if I use the numerical values, 10 grams, 12 centimeters radial distance, 100 degrees of theta r used to mount the reference mass, and 30 degrees, which is the measure of the between the two lines of equilibrium L1 and L2, and this gives me the unbalance, the product MXLX, which is 225.526. Okay, now with this value, I choose for convenience values of angular position and radial distance for the reference masses, for the balancing masses. For example, if I choose theta 1 40 degrees, theta 2 50 degrees, L1 12 centimeters, L2 12 centimeters, with these values and the value of the imbalance, I can compute the values of the balancing masses that I need to place. And just by replacing the numerical values in these expressions, I compute that for M1 I need 12.1 grams, and for M2 I need 14.4 grams. So obviously, or most likely, you won't have exactly balancing masses of this magnitude, but you can approximate them, maybe 12 and 14, and fill in using like a Scotch tape or electric tape, and that'll give you allow you to complete the exact value that you need. Okay. Okay. Thank you very much for your time. I hope it was useful. I hope this method for balancing rotors could be useful to you in the future. Thank you very much.